At least wire field view, right? Oh. Right.
Just to let you know, I'm doing a profile piece on mechanics. So I'm going to film this.
Yep. 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 Yeah.
We'll do about 10 minutes to start. Sure.
Shall I fill a minute, or should we just start?
Yeah, we could start. And I can get this uploaded while I'm going through.
Okay. Only if I have some. Oh. Yeah. I'm gonna make this thing go. Very plugged in, but not very long. You may have to, because I can't.
Hi. Hello?
No.
Can anyone hear me except for the front row? Interesting.
Oh. I don't know how to control that.
We're not sure. We need some help. We're not the sound area.
Does this microphone work? No, I think this one doesn't either.
Yeah. None of these are light.
Oh, maybe someone was meeting in here and turned off the sound.
No, this guy seems to think.
Oh, where are they? Here they are.
I'll ping Alexa. I think that guy was trying to think about it, but I'll ping Alexa. Oh. Okay.
Thank you.
Yeah, good call. Projector's like in a terrible location. I don't really know why we waste a whole screen on Pac-Man.
Do you have a preference?
No, take whatever you want.
I'll go fizzy.
Sounds great. Thanks.
Yeah. Drink with me too. I'll just speak loud. Do we have a volunteer Jabber scribe? It's the only thing we need. Okay, great. Thank you, Ted. And thanks to the 2 minute taker volunteers. Joe and Uran. And before we start, if you're not here for SAAG, that's what we'll start doing as soon as we have audio.
Raz, dva, raz, dva, raz, dva, raz, dva. Raz, dva.
No, dobrý, už jde. Stand už, že?
Raz, dva.
Yeah, we have Mike.
Hello?
Okay, hi, welcome to SAAG. I'm Eric Pasquarla.
Kathleen Moriarty?
So I guess we're starting with working group reports. Actually, starting with note. Well, I forgot. You all ought to be familiar with this. If you're not familiar with this, well, I guess you can read it or read it later. Right, so we'll start with some working. Barry, did you have a
Working group report.
Yeah, okay, good. Just didn't know
If you're doing them in order, I'll wait.
no. Well, we are doing them in order, it turns out. Ace?
We met Monday morning, and we have lots of different proposals floating around on how to carry these different tokens around into the authentication and authorization. So we had lots of researchers coming along and providing input. We unfortunately didn't make that much progress on the already charted items, so we need to improve on that. But there's a lot of ideas.
Thank you. So Acme sent the report. Curdle, thank you. Also sent the report. Dots, thank you for sending the report. I2NSF.
So we met Thursday. We actually have two sessions. One is a pre-session and then a formal session. So this time we had lots of contributions on the data models and information models. So this meeting mainly is to make sure they align with each other. So we reached a really good result on that. Thank you.
Thank you. So IPSecMe sent a report. Thank you. Kitten sent a report. Thank you. Lamps. Oh, okay, I missed that. Thank you. Miles sent a report. Yes, no, I'm saying you sent a report. Thank you. OAuth, I didn't see one. Hannes, this seems to be a pattern.
Yeah, actually, the final session is tomorrow. So the first session we talked about wrapping up some existing working group documents, and we also had Mike Jones present a best current practice on a JWD after some researchers found attacks. So we documented those, and we did a hum, and the group wanted to work on that document, so that's something we will confirm on the mailing list. So if you use JWDs, that may be a good document to look at, or if you implement them.
All right, thank you. And OpenPGP.
OpenPGP has had quite remarkable success in not getting anything done. And that has resisted all attempts from both chairs to talk to people offline and try to poke things. And so we have asked Eric to close the working group whenever he is ready to do that, and told the working group that, and hope that that might spur some things. And it spurred a few words, but no actual action. Eric, any comments?
I think I'm happy to do so, I suppose. Thank you for your service.
You're welcome. And I would say happy to do it isn't quite the right characterization.
Sorry,
but no, I understand. No, I'm just saying I'm sad that we could not get it done, but in fact we cannot. So.
Yeah. And as the co-chair, this is DKG. I'm also bummed that we didn't manage to get that done. There is continuing work in that space probably, and if I can manage to get people to document it, I'll try to get them to submit drafts. And if they actually start submitting drafts that are actually functional, then maybe I will come back and ask for more. But we have not had any luck in getting it to move. We don't have enough implementers in the group right now, I think.
Certainly OpenPGP is a protocol people use, so if it turns out to be a case that you have activity that's worth your standardizing, we can figure out some way to we create a new working group. OpenPGP 2, I think. 3? All right.
All right, Sackham, thank you for sending the report. SEC event, I didn't see one. Oh, it is sent. Okay, thank you. My mistake. And TLS, thank you for the report and the nice management of a tough working group session. Tokebind?
Yeah, I didn't send a report. We met on Monday. Core documents are in last working group last call. We're playing around a little bit in proxy hell with a draft that may involve some help, us needing some help from the HDP working group. We'll see.
And I think we did get one from Tran, so thank you. So now we're going to go into related working groups, but we're going to do a little interrupt in the middle of that for one of the related working groups. Lionel? Thank you, great. He's going to talk about a need that we've brought up before in SAG, and we have a request.
Okay, thank you. So in the DIME working group, so we have the base protocol, and initially in the previous version of the protocol, we have end-to-end security stuff. And when we published a new version of this one, this end-to-end security mechanism was deprecated. It was based on CMS, and nothing was done. So we are still looking for a solution for end-to-end security. Basically, it could be between edge agent. Between two different networks, and you will go through what we call a roaming network. So you have a bunch of agents in the middle. So, or you may have end-to-end, real end-to-end communication between two clients and server. So the idea is to have a solution to be able to protect AVPs. Next slide, please. Yeah, so the status is that the end-to-end security requirements is now an RFC. So we have existing requirements coming from the mobile community, so for roaming especially, but also by operators that would like to protect their diameter signaling. So what we have done is to reuse a previous draft called end-to-end security, but no work was done on this one. So there is a lack of resources and also lack of expertise, because we have the diameter part, but we have also the security aspects. Next slide, please. So we have in the existing draft, we have a basic solution where it's possible to have integrity and confidentiality. So what we're defining, it's a specific AVP where you are able to sign, and another one where you're able to group all the sensitive AVPs and to encrypt them and to put this in this what we call a group AVP. So it's how to be able to convey this information. So the solution was based on JSON. So using the JSON web signature for the integrity protection and web protection for the confidentiality. We were thinking about maybe there is something new to do in this area, maybe instead of JSON using CBOR COSI. Or if there is any other alternative. So next slide, please. So I'm here because we are crying help.
Yeah, sorry, I added the note per other feedback. I think it just threw you off a little.
And so I think that the proposal is quite simple, just to be able to have a solution. So I know that people in the room are aware of this issue. So I'm looking for some guys that could help on this work. So we could create a kind of a design team and so on, just to be able to have a solution done. So any volunteers will be welcome. So you can contact Catherine, myself.
And are there any volunteers in the room that are interested in helping on this? Okay.
Please help.
Yeah.
This is Jean Mahoney, have been in the DIME working group, and yes, this has just lingered. It's been pushed off. We're losing energy, and we're realizing we can't do this by ourselves. So would like some volunteers. Thanks.
Philhan Baker. I had to generate something very similar for my mesh work. It's written up, but not separately from the other stuff, but I can pull it out. I did notice the problem with applying Jose encryption, and rolled my own based on Jose, but doing things in a more sane fashion for doing end-to-end encryption. within a web service. So
you're willing to help?
Yeah.
Okay, hopefully we have a few more people. Thank you. And we'll move on to this is an eye chart from here. We'll move on to the rest of the related working groups. So Anima, I saw a report. I don't have a nice list marked up, so I may not know all of these. D-Bound. Oh, okay. Dime. We just got that. Dispatch. Anything for dispatch? Okay. DMARC?
DMARC met this morning, and I guess the main thing that it's discussing right now is whether to put out the document as experimental first or go straight to standards track. We'd originally been figuring standards track, but Dave Crocker pointed out that we don't know the operational effects of what we're doing and could use an experiment with that. So the working group still hasn't decided that, and we'll figure it out. Otherwise, it's almost ready for working group last call. That's the ARC, sorry, that's the ARC spec. The DMARC spec itself is informational, and it's on our queue sometime to think about moving that to standards track, and whether we will do that or not, we don't know yet.
Thank you. Deprive, HGBiz, Quick, NetConf, NTP.
I just wanted to give one quick update. The network time security specification is going to go to working group last call this week, or the current draft is going to working group last call. And last time when we sent it to working group last call, the security community was very responsive, and we're hoping you will be so again.
Thank you.
Can I jump in about Deprive?
Please.
So the big two topics that we talked about when we met were, we had a bunch of fun and games talking about DKG's proposal to demux DNS and HTTP traffic on port 443 to the same server. That's good watching if you want to go back and look at the videos. We also had a really interesting conversation about DNS over Quick within the context of privacy. So I think we got some really interesting feedback on that draft as well. And we touched again on how do we move forward to look at the recursive to authoritative problem, but we haven't got anything concrete there yet.
Lars, good. I co-chair Quick. We are monitoring the situation in TLS with interest.
Let's see. PERC and RADX. Oh.
So PERC is getting around some of the issues it had with its double context encryption for RTP. That's getting to a point where it would benefit from some more review. Well, probably in a couple of weeks once the new draft is out, would benefit from some review from folks who are cryptographically minded and have some enthusiasm for real-time protocols. So yeah, like I said, I expect there will be a new version of that double encryption draft in a few weeks. And then I'll maybe ping the SAG list for some more reviews.
Okay, and so for RADX, they'll just say they're going to close soon. They are going to work on, I think, one more draft and get that through the working group and likely close. So thanks to everyone for their work on that. CIDR, TCP Inc., I think, sent one. Yes. And Utah.
All right, we're meeting later tonight, and we can sort of start to see the light in the end of the tunnel. So by, okay, talking to somebody else. Right now we've got the core documents that we were chartered to do. They've been RFCs for a while. We're working on a few specs related to the best practice of using TLS in email. Various forms and shapes, but after that we can't really see any other work. So if the security community has stuff for UTA, you should bring it to our attention before Singapore, because after that I think we're gonna be done.
Thank you. Okay, CFRG.
No, you forgot decrop.
Okay, we did.
Yeah, kernel for DKIM. We have 3 documents almost done. Deprecating SHA-1 and 512 RSA, using ED25519, and I forget what the third is, but we'll probably be done really quick and not meet in Singapore.
All right, thank you. And sorry about that. So CFRG. Okay, thank you. IRTF open. PrivSec.
So we've changed chairs. It's actually Martin now, but I'll give a quick report. The PrivSec is currently looking at developing a traffic analysis document that catalogs different forms of traffic analysis and provides sort of guidance to the community.
Thanks, Ted.
At IRTF Open, one of the 2 talks is Stephen Checkaway on breaking Juniper's DRBG. So for those security people not going to quick, they may want to go hear one of the research prizes.
All right, thank you. And W3C? We didn't have any BOFs, so now we're going to move on to presentations. Oh, yes, sure. So we have BOFs from the previous one where there is work going and a report was sent, but both TEEP and FUD.
Yeah, for TEEP we had a tutorial on Sunday, which I think was well attended, describing on how Trust Zone works and the scope of the TEEP effort. On Wednesday we met to discuss the charter, and I posted it to the TEEP mailing list. And we will also continue with the webinars. So there will be a webinar from the Intel guys about their trusted execution environments. Hopefully maybe next week or the week afterwards. I'm still talking about the exact date, and I will send a doodle poll around and we'll make the announcements. For FUD, which is about the firmware updates for IoT devices, we actually met today, a sort of a side meeting to talk to those who are developing operating systems for IoT devices, who are the potential customers or the potential guys who are impacted by this. And there are 2 new documents out there posted on the mailing list describing what the standards effort could look like. And so please join that list if you care about firmware updates and or IoT devices.
Thank you. And we are hoping to charter those at least soon, before the next meeting or after a BOF at the next meeting.
I thought I'd give you the W3C update a moment
thank
late.
you.
Sorry, I didn't realize I was on the agenda. This is Sam Weiler. W3C's Web Authentication Working Group is making interesting progress bringing token-based, device-based authentication up into the browser. But I think the thing that'll be of more interest to the room is we're reaching out and trying to get more eyes doing security and privacy reviews on our specs. If people in the room have interest in that space and are interested in reading some W3C specs with an eye towards security and privacy and maybe stopping our working groups from doing stupid things, please get in touch with me.
All right, thank you. So now we move on to presentations, and Kenny Patterson's up first with a presentation on post-quantum crypto. So we're just going to switch laptops here.
Yep. You want me to just next for you, Kenny? Make it double. There you go, sir. What's your password?
So you can call me sir.
That's
what that works. Okay. Okay, good to go. How long do I have?
30 minutes.
Okay.
Right?
So 30 minutes on post-quantum cryptography. I promise you there are no equations in any of my slides. So if you were thinking of making a run for it because of the possibility of equations, you can stay in your seats. I'm going to start by looking at something that's manifestly not post-quantum. I'm going to start by talking a little bit about SHA-1 and talk about the lifetime of SHA-1. So we go back to deepest, darkest history, the 1990s. SHA-1 was published. It was actually a tweak of a design from 1993. There were various attacks on SHA-0 in the 1990s, which validated that switch. Then SHA-2 was published by NIST in 2001. Nobody used it. We had the first collision attack for SHA-1 in 2005, except it was an attack that didn't provide any collision. It was an estimated complexity of 2 to the 63 hash operations. There's a famous breakthrough paper by Wang et al. It's maybe worth remembering that Wang was denied a visa to come and present that result in the United States at the time. Some things don't change very much. Then between then and now, there were lots of claims and counterclaims about improvements to this attack and re-estimations of the complexity. In 2006, NIST took the step of deprecating SHA-1 from 2010 onwards for all federal agencies for all new applications requiring collision resistance, so a limited set of applications and use cases. In 2013, Microsoft got around to doing something about SHA-1 deprecation from 2016 onwards for new code signing certificates. 2014, still no collisions, so this is now quite some time, nearly 10 years after Wang's paper. Wang et al.'s paper, I should say. The best estimate at this point in time is 2 to the 61 hash operations to compute a collision due to Mark Stevens and his collaborators. In 2015, something really interesting happened. We saw something called free start collisions, which are a precursor of full collisions against SHA-1. Not quite there yet. Requiring moderate computation, 10 days on a GPU cluster with 64 GPUs. 2017, SHA-1 is still widely used. There's lots of activity in the CA browser forum. Maybe some of you have seen some of that lovely controversy happening over there, resisting the removal of SHA-1, trying to extend its lifetime and so on. And then finally, we got the first collisions in SHA-1 in February this year, a joint research activity between the researchers at CWI, led by Mark Stevens, and by Google. They finally actually exhibited SHA-1 collisions, cue much press coverage, and then lots of researchers like me saying, well, you knew this was coming. This should not be a surprise. 6.6K core years of computation, so 6,600 cores running for a year, some permutation combination of that kind of resource. So pretty serious work required. Then what? Well, we'll see what happens. I think SHA-1 will be with us for some time to come. Indeed. Here's a related graph that shows the uptake of SHA-2 in browser trusted certificates on the public internet. And you see that SHA-1 certs, which is the red line, suddenly started decreasing in and around early 2014, and then SHA-2 started to shoot up, and MD5 has effectively reached 0, which is a good thing. Anybody want to guess? Yeah, by all means, applaud, applaud. Let's make this as interactive as you like, except please don't throw things. So anybody want to guess what happened in early 2014 to make this thing tick up? Heartbleed. The first vulnerability with a logo. Not the last, only the first. Okay, so I think what's important to say here is it was not a cryptographic attack that led to the switchover from SHA-1 to SHA-2 in certificates. It was a computer security vulnerability in a very widely deployed piece of software, OpenSSL. Okay, what about progress in quantum computing? We've seen something happening in the kind of classical world. I apologize for the very small font on this slide. I think the slides are online if you want to have a look at them and follow along. So there were so many things to put in here. There's been so much progress that I had to make the font very small. So it's interesting. I got all of this from Wikipedia because I am not an expert on quantum computing or quantum physics. I actually missed that class in physics. So pre-1994, Wikipedia says that there were these isolated contributions by various great physicists, people like Stephen Weisner, Halevo, Charlie Bennett, etc. Lots of interesting little nuggets, but no kind of connecting theory, no kind of concept of quantum computing as a thing. That really changed in 94 and then 96 because of Shor's algorithm and Grover's algorithm. So Shor's algorithm basically breaks discrete log and factoring problems with poly-many gates and polynomial depth, polynomial in the size of the numbers that you're working with. In other words, all public key cryptography deployed on the internet today is broken if you could build a large-scale quantum computer that could implement Shor's algorithm. And Grover's algorithm in 1996 basically gives you a square root speedup for search problems, and the effect of that is to half the effective key size of your symmetric primitive. So some would say that's why we have AES256 in the first place, as a hedge against quantum attacks and Grover's algorithm. In 1998, a 2-bit quantum computer was built, and 3 bits using NMR. In 2000, we got to 5 bits and 7 bits using NMR. In 2001, so this is great, the number 15 was factored. No, seriously, on a quantum computer. I'm not I'm not making a joke here. This is significant progress because it means you have to build a large enough computer and run it for long enough to find out that 15 is 3 times 5. The qubit was announced in 2005. I have no idea what that announcement means, but it's good publicity. In 2006, we got to 12 bits, 12 quantum bits, 28 quantum bits, and now you start to see a runaway. 2008, 128 quantum bits. This stuff just got real. This got really worrying, except this is D-Wave. So there's some knowledgeable laughter from the front. For those of you further back, what D-Wave are building is a quantum annealing machine. So it implements some kind of annealing algorithm in a quantum way. It's not doing general purpose quantum computation. You couldn't use, as far as we know, one of these D-Wave computers to run Shor's algorithm, for example. We do know that Google bought a D-Wave machine. Anybody from Google here willing to confirm that? And then tell us what you're doing with it? I have been told that they dismantled it and rebuilt it in their own image to somehow do their own stuff. So they have those kind of people. Okay. Yeah, true. Okay, so back to the real world of actual general purpose quantum computation. 14 qubits in 2011, and then in 2012, the number 21 was factored. That's 3 times 7. And then actually, between 2013 and 2017, there wasn't a huge amount of kind of publicly announced progress in factoring. And I've been told by experts in the field that's because factoring is the wrong problem to focus on. We should be looking at other things than factoring. I think it's because they found it hard to scale their quantum computers beyond the number of bits they needed here. They're instead focusing on more fundamental technologies, trying to get them in place before attempting to factor larger numbers. In late 2016 onwards, the physicists did a pivot. I believe it's called a pivot in the tech world, towards focusing on something called quantum supremacy, which is actually a phrase I find personally objectionable. It has a lot of really ugly overtones, the use of the word supremacy here. And what this means is building a large enough quantum computer that you could solve a problem that no classical computer could solve in a reasonable amount of time with a reasonable amount of resources. Think of pooling all of Google and Akamai and Cloudflare servers all together, trying to solve some computational problem, not being able to do it, but being able to do it on a quantum computer. Something like some kind of quantum chemistry simulation, for example. And so now there are rumors, there are circulating around in the research community that quantum supremacy will be announced. At a conference in Berlin last month, Google announced that they would achieve quantum supremacy by the end of the year. But I think that's using one of these, well, who knows exactly what that means. Let's not speculate too much. In 2017, D-Wave launched the 2000Q, which has 2000 quantum bits in their simulated annealing world. That reminds me of the story of Hewlett-Packard, whose very first product was called the Hewlett-Packard 200. Okay, because it sounded good to start with something that had a large number in it than a small number. It looked like you were more established. I guess D-Wave have been around for a while now. IBM unveiled a 17-bit quantum machine, sorry, a 17-qubit machine, and Google and Microsoft Research are all doing cool stuff in this area. So there's a lot of energy going in, a lot of money going into this. Progress, hard to judge for me. So what I'd say is that to draw these two things together is that the threat of large-scale quantum computing is kind of weakly analogous, and go with me on this, it's a pretty weak analogy, to the threat of a breakthrough in SHA-1 collision finding. The breakthrough might be imminent, but then again it might not. And we now do actually have SHA-1 collisions, so this slide really should have been updated. But for a long, long time, people were speculating, well, we can do SHA-1 collisions, but nobody's done it yet because the reward is not high enough or because it's actually harder than we think. We didn't really know whether it was going to be possible or not. We didn't really know whether those algorithms would scale or not to the size required. It's hard to quantify the risk that something will happen and hard to put a time frame on it happening. But meaningful results in this area would have a substantial impact, and lots of smart people are working on it, and there's been a tremendous amount of research investment. On the other hand, maybe quantum computing is a bit like fusion research. Have any of you tracked fusion research over the years? It's been very interesting. There's been tokamaks, and there's been all kinds of plasmas and firing lasers at pellets, and none of it really works yet. Okay, so here's some conversations I've been party to with people in the quantum computing world. Large-scale quantum computing is only a decade away, but they've been saying that for 25 years. Okay. In terms of fundamental physics, we're pretty close to what we need. There's just tons of engineering work. And this is a quote from Evan Jeffrey, who is now with Google, was with UC Santa Barbara, and he and his team were acquired by Google. And this was in a really great talk that he gave, a very cold-headed, sensible talk that he gave about quantum computation at Real World Crypto in 2017. And you can find that on the Real World Crypto YouTube feed. And he estimated also in that talk that to break a 1024-bit RSA modulus would require something like 250 million quantum bits to be held in a coherent state for long enough to do the computation. I'll just remind you the current state of the art is 17. So there's a gap. But apparently, it's only engineering work. Okay. We should get him to come and say that to the IETF, right? See how you guys react to that. Yeah. Okay, so is there a coming crypt apocalypse? I should never put a word on a slide that I can't actually pronounce. I find apocalypse very hard to say. I've done it twice correctly now, and I think I'll quit there. We don't know whether there'll be a scaling breakthrough or not. If it comes, it would be pretty catastrophic for the internet and for internet security. So, as I mentioned before, Shor's algorithm would mean that all currently deployed public key cryptography on the internet today would be broken without exception. Okay, you can break elliptic curve cryptography, all discrete log-based cryptography based on finite fields, all RSA-based cryptography, and that's pretty much what we have in deployment today. Interestingly, because of the key sizes and the sort of scaling properties of quantum computation, elliptic curve cryptography would break before RSA. So elliptic curve cryptography is weaker for the same key size, for a smaller key size than RSA. And one of the things to think about here is that an attacker, a well-resourced attacker, think nation-state adversary, NSA, could capture interesting. Okay, you're catching up. Good, good. Okay. A nation-state adversary could capture interesting-looking Diffie-Hellman exchanges now. Okay, so from my mail server to Eric's mail server, where we're discussing this talk and what am I going to say? I think there's a question.
Yeah, just a quick question on the ECC point. It seemed, Richard Barnes, has this been a point that has actually gotten some analysis besides the hand waving keys are longer, need more qubits? Because there are like time-space trade-offs that apply here. And so even though you might be able to get by with fewer qubits, you might need a longer coherence time and hit the similar walls.
I think a detailed analysis of this was done by some colleagues of mine when I worked for HP back in the 90s, HP Labs. I think if you look for the name Tim Spiller, you might find a little white paper that describes this phenomenon. Yeah.
Paul Hoffman, to answer, there was just a paper like 2 months ago on this, which actually says that maybe ECC is going to be almost as hard for equivalent strengths. Okay. The last thing I heard was you need many more registers, so you need a bigger computer. I believe the answer is there's not agreement yet. There probably will be agreement on this within the next few years.
Thank you very much for that clarification, Paul. Okay. As I said, I'm not an expert, so if people here know more, please come and grab the mic and give the rest of the presentation. That would be really great. I could sit down. Okay, so we would expect some warning of impending disaster. We would hopefully see in research papers, published research, but of course you don't necessarily know what's going on inside the government research lab. And we know that replacing crypto at scale takes time. Okay, it took a long time to get rid of Mac then encrypt in TLS. It's still hanging on in there. I think we kind of killed RC4, but still it takes time, and you'll still see it in, I don't know, corporate data centers where they don't really keep that up to date with security. No, sorry, I didn't say that. Okay, replacing crypto at scale takes time. And of course, as I mentioned, traffic capture now could be broken later. So if you've got data that needs to be kept secure for decades and you think there's a risk of large-scale quantum computation, then you need to apply some kind of precautionary principle and think about migrating your crypto sooner rather than later. Okay, there's even a conference for this. It's called Catacrypt. It's a pretty doom-laden conference, but you know, if you could go. Okay. Okay, so how should we move forward from here? Well, this is not the way to move forward. Let's think about post-quantum cryptography instead. What is PQC? Post-quantum cryptography is cryptography based on conventional techniques, so conventional public key crypto systems. These would compile on your computer and run, okay, on a classical computer in a reasonable amount of time. And we believe, to the best of our knowledge, that they resist the known quantum algorithms, so Shor's algorithm and so on. So this area is called PQC, and sometimes it's called quantum safe cryptography, sometimes it's called quantum immune cryptography. If you work in the area of quantum key distribution and you're a physicist and you want to embrace post-quantum cryptography, then you call it quantum safe. Okay, it's a way of bringing other things into your fold and extending your reach and so on. So there's a little bit of politics here. We're going to call it post-quantum cryptography. The main candidates for this, and this is where I would have had the equations had I been braver, are lattice-based cryptography, which has been studied for around 20 years now, I think. Code-based cryptography, which has actually been studied for much longer. The Macaleese code-based scheme uses GOPA codes. These are error-correcting codes, and it was already in the late 1970s, early 1980s being proposed and explored. There's newfangled stuff based on nonlinear systems of equations. They have a pretty patchy history. There's been a lot of schemes proposed and then broken. We're still finding out what makes these problems hard. And then the latest, greatest thing is elliptic curve isogenies. If I was a tech investor, I would not invest in elliptic curve isogenies right now. They're extremely new, and we're still really figuring out what kind of security they offer. So there's 4 main approaches that the researchers are currently exploring. And these different approaches, they could be vulnerable to further advances in quantum algorithms. So it could be that tomorrow Peter Shor comes up with a new algorithm that solves hard lattice problems. We simply don't know. What we do know is that smart people in the quantum algorithms community have been working for a long time to develop new quantum algorithms, and so far, with one exception, they have not applied to lattice-based schemes or to these other schemes. And the exception is this paper by Elder and Shor that was published much earlier this year and then almost immediately withdrawn because there was a bug in the paper. It was a very unfortunate thing, because this was the first time that somebody of Peter Shor's stature had something interesting to say about lattice-based cryptography. And this was kind of a wake-up for the classical cryptography community. This was a very interesting piece of news. It turned out that the parameters that he was able to attack using his quantum algorithm were not the parameters that we would use in cryptography, but still it was maybe the first quantum chink in the armor for lattice-based crypto. So this was a significant thing, but as I say, the paper was withdrawn. But maybe he'll come back with a new idea with working with Eldar in the future. We just don't know. There was also a paper published by GCHQ in the UK, now renamed as NCSC, called Soliloquy. And this was an explication of their failed attempt to build a lattice-based crypto system that was quantum immune. They found a quantum attack against their particular scheme. So there was another data point there for you, that maybe this stuff has some ways to go before we really understand its security against quantum algorithms. Even the conventional security of these schemes is not well understood in all cases. We have a pretty good handle on the security of hash-based signature schemes. For example, XMSS, which has been working its way through CFRG and is close to being an RFC now. There's a later scheme called Sphinx, which is developed by some academic researchers a couple of years ago. And we have a pretty good handle on how to choose parameters to make these kinds of things secure. They rely on pretty standard properties of hash functions, which we believe are not really susceptible to quantum attacks. We even have some lower bounds for the strength of quantum attacks against these things. But for things like lattice-based crypto and code-based crypto and nonlinear systems of equations, the academic research community is really now digging its hands into this area and trying to figure out exactly how we should set parameters and improve attacks and so on. And I'll just pause there because I see Stephen coming to the mic. Stephen.
Hi, Stephen Farrell. So for the hash-based signatures, I don't know if this is true for all schemes, but for some, the more mature ones at least, you only get to sign a relatively small number of times, and then you have to change private key. Is that correct for all?
It's a question of parameter selection. And yes and no. I mean, there's trade-offs between the number of signatures you can sign and the size of signatures and the cost of signing and so on. I think on the next slide, I'll come to this point, talk about some of the characteristics of these schemes, and maybe I'll try and address it there. Okay, yeah, here we go. So it's true, and this is really what Stephen is hinting at, that the current post-quantum schemes that we have are not as performant as the pre-quantum schemes. We've all got very used to elliptic curve cryptography, not really consuming that much power on our servers, or not that much bandwidth on our networks. So typically what you're going to find in the future is larger public keys and larger key exchange messages, larger ciphertexts, etc. I don't have hard numbers for you here. We can discuss that later if you want. This field is still very much evolving. On the flip side, you actually often get much faster cryptographic operations. To actually do an encryption with some of these lattice-based schemes is just a matrix multiplication and adding some noise vector. So encryption is much easier than some kind of finite field exponentiation, for example. This is good news. The performance may suffer as we refine our understanding of how hard the hard problems are in this area, as we refine our understanding of how to choose parameters for security. So better attacks, which will emerge over time as people tweak their code and come up with new ideas, imply that larger parameters are needed for the schemes. And that can also lead to particular approaches just being completely abandoned. So we've seen that a lot with some of the systems of equations approaches. People had ideas, they tweaked them, and eventually they said, okay, we give up. We can't make this secure using this current set of ideas. And parameter selection in this area is a much more complicated question than it is for RSA and ECC. We've got used to magic numbers like 2048 bits for RSA or 3072 bits if we're crazy about security, or 256 bits for ECC. There are more parameters to play with in the post-quantum schemes, and it's harder at the moment to figure out exactly how to set them. Put another way, we're roughly where we were for RSA in about 1982, okay, I would say. I wasn't around, I mean, I was born then, but I wasn't doing cryptography then. I was just out of short trousers. But looking back in the literature, there was a lot of debate about exactly how big our RSA should be, our RSA number should be. Can we choose E to be small, or can we choose D to be small to improve decryption, et cetera, et cetera. Okay, so we're kind of in that phase at the moment in the research community. Okay, how am I doing for time?
8 minutes.
8 minutes, okay, I'm going to speed up a little bit. So where are we right now with post-quantum cryptography? We are still doing research, lots and lots of research. And we're progressing from research towards standardization and deployment at a fair rate of knots. So there's a couple of examples here. There's something called the Internet Defense Prize, which is awarded at Usenix Security each year. And it was given to a lattice-based key exchange protocol called New Hope in 2016. So the industry was like noticing this stuff was happening and rewarding it. New Hope was then experimentally deployed by Google last year in SSL TLS. You can read about that on Adam Langley's blog. It's been switched off now. It was a limited time experiment to understand the impact on bandwidth and processing time. And there's a huge amount, an increasing amount of mainstream crypto research going on at the moment in this area. But we're not there yet. And on the standardization side, NIST last year announced a process for standardizing post-quantum public key algorithms. Announced in 2016, the closing date for your submissions, if you're planning to make one, is November the 30th, 2017. And I know there are lots of academic and industrial research lab teams now getting their proposals together, fine-tuning them. I'm going to be involved in one myself, so for full disclosure, I have a dog in this particular fight. The process is going to run, as I mentioned, up until 2023-ish, and the evaluation criteria are security, naturally, cost, and then this kind of mixed bag of other sort of secondary criteria: flexibility, simplicity, and adoptability. And you can go read on the NIST web pages to figure out exactly what this means. And here's a rough overview of the process. And I don't want to go through every single one of these steps. I just want to show you how long the process is expected to run for. So think back to the days of standardization of AES and add an extra 2 or 3 years to that. And then at the end of that, we may have a portfolio of post-quantum algorithms that we can use. Or NIST have reserved the right to make a decision that further evaluation is needed. Okay, so it's going to take some time. Hang on, you're thinking. I've heard about this thing called quantum cryptography and quantum key distribution. Why are we not using that instead of post-quantum cryptography? Well, let me destroy quantum key distribution. Nah, destroy is too strong a word. Let me critique quantum key distribution. Okay, so this is great, right? This is, the physicists will tell you, this promises security based only on the correctness of the laws of quantum physics. And the correctness of quantum physics is not in doubt. It's been verified to 10 decimal places. By the way, 10 decimal places is not very large when you're thinking about security parameters for crypto. Okay? We consider an attack at the level of like 2 to the minus 120. Then we scrap your block cipher. So 10 decimal places doesn't really cut it. Anyway, okay, and this is often contrasted to the security offered by public key cryptography. You know, it's said that public key cryptography is vulnerable to quantum computers and quantum key distribution would not be, et cetera, et cetera. I got some quotes together here. This is from Brian Lowndes, Dr. Brian Lowndes from Kinetic. Quantum cryptography offers the only protection against quantum computing, and all future networks will undoubtedly combine both through the air and fiber optic technologies. Okay, here's another example. All cryptographic schemes used currently on the internet would be broken. That's not actually true. This was said by Gilles Brassard, who is an IACR fellow and ex-editor-in-chief of the Journal of Cryptology, so he's a pretty solid cryptographer. And he said this at a launch meeting of some institute. This is an early example of alternative facts. Here's MIT Technology Review as early as 2003. This is QKD is one of 10 emerging technologies that will change the world. Even Bert Kaliski, who many of us know and highly respect, said back at this time, if there are things that you want to keep protected for another 10 to 30 years, you need quantum cryptography. These are examples that I gave at a talk 10 years ago this year at the Fields Institute at the University of Toronto. So these are all 10 years old. So what's the big holdup? Why are we not already using quantum key distribution? Well, I'll give you 4 reasons, and I have backup slides, so if anybody wants to debate this with me, let's do it in the coffee break after. QKD doesn't actually do what it says on the tin. It doesn't distribute keys, it expands existing keys. And if you already have a key in place, you can expand it in all kinds of ways and build as many keys as you need to, using things like key derivation functions. Okay? QKD has significant limits on both range and rate. Range is the most fundamental one. You may have heard about the Chinese quantum key distribution network running from Beijing to Shanghai. It sounds very, very impressive, but it does not provide end-to-end security. It's a sequence of links joined together. And at each intermediate point, you can read the traffic in the clear. Okay? If you want end-to-end security, QKD is not going to give it to you until we have quantum repeaters, but they require quantum computers, and I think I've told you about quantum computers already. Security in theory does not imply security in practice. In theory, they're the same. In practice, they're not. I think Yogi Berra said that. Here, the idea is that we have to build devices. We have idealized models of the physics, but the devices will have weaknesses. They'll have side channels. You can shine laser beams into single photon detectors and cause them to go haywire, et cetera, et cetera, et cetera. Okay, so building secure systems is different from designing secure systems. And finally, quantum key distribution does not offer significant practical security advantages over what we can currently do at low cost with conventional techniques, by which I mean symmetric key cryptography. Okay, check me later if you want the details on exactly why that's true. Okay, it's not just me. This is my government. This is the view from NCSC or GCHQ, as was quantum key distribution. They actually took the unusual step of publishing a white paper about 2 years ago, outlining their view, and here's what they say. The summary is that QKD has fundamental practical limitations, does not address large parts of the security problem, and is poorly understood in terms of potential attacks. By contrast, this is wonderful, this is catnip for someone like me. By contrast, post-quantum public key crypto appears to offer much more effective mitigations for real-world communication systems from the threat of future quantum computers. In other words, invest in PQC, not QKD. Okay, coming close to the end now. What should the IETF do? So CFRG is on this to some extent. We're looking at developing internet drafts for hash-based signatures. We've got 2 drafts in development at the moment. One is very close to being finished. And as I said before, this is a very mature and less risky area. But I think that all the other post-quantum schemes are still in that kind of difficult teenage phase, right? Where they're kind of gawky and awkward and likely to lash out at any moment. And that's in the research community, never mind standardization and actual experience of deployment. So we have a long way to go here. And my view is that NIST's process is where the action is going to be. So NIST has the resources, the secretariat, the experience needed to run a proper process. You might think back to things like the Julie C fiasco, and maybe NIST is not the body that we should trust to develop our crypto standards. But I believe that isn't a significant concern here because of the very heavy involvement that the academic community will have. I hope that, and I believe that the academic community can keep the process honest. And the scientific experts will all be concentrating their efforts there with NIST and not with IETF or other standards bodies, at least in the next 5 to 7 years. That's where the action is going to be. So I think, my personal view, this is not a CFRG view or anything else, just my personal view, we should wait for NIST process to run its course. We should be ready to roll over once those algorithms are finalized. We should continue to avoid baking in any algorithms, so we should have algorithmic flexibility. The ways that we can get that wrong, for example, are having maximum field sizes that are rather too small for post-quantum algorithms. So we should avoid doing things like that. We should keep an eye on the kind of flows and the protocol exchanges that are involved in key exchange algorithms, post-quantum key exchange algorithms. They're not as simple as straight up elliptic curve Diffie-Hellman would be. So that's going to have an impact on protocol latency and round trips. So we might need to design carefully to avoid impacting on those things. We should also maybe do some work, and CFRG could do this, understanding how best to combine or classical crypto systems with post-quantum schemes so that we get a hedge against a failure of either type. And we should also identify and resist any efforts to do the kind of SDO shopping that you sometimes see, where people go to multiple standards bodies until they get one that takes their stuff. And we should allow NIST to do its work with the help of the scientific community. Okay, so final slide. It might be coming or it might not be. I'm not going to try and say that word. It's possible that post-quantum crypto is a massive misdirection of the scientific community, designed to distract us from things that really matter, like weak Diffie-Hellman parameters, or, I don't know, maybe repeated ephemeral values in the TLS protocol or something. Sigh. That makes me so sad. Makes me so sad, folks. I'm channeling Donald Trump there. So we can hope, and I believe that in this process will proceed in an orderly fashion. They're actually, in some sense, staking their cryptographic reputation on it. They have to get it right, and they have to put adequate resources into it, because they're still in the process of doing a repair job based on what happened with Julie C and that whole fiasco. So I think at the end of it, we will see a very sensible and conservative portfolio of algorithms, of options that will suit IETF's needs. In the meantime, there's things that IETF can be doing, as I mentioned on my previous slide, to make the transition as smooth as possible, so that when we get those algorithms for NIST, we're ready to start using them. Okay, so that's everything I wanted to say. Please form an orderly queue at the mic, and I'll be happy to talk to you. Thanks a lot.
So thanks for the overview, Kenny. This is Richard Barnes. I will +1 the suggestion on your previous slide that CFRG take a look at this question of how you combine classical and post-quantum algorithms, or pre-quantum and post-quantum algorithms, if you will, because I think that's going to be critical to transition. And I think it was one where we're developing a solution with some degree of generality. I think it would be really useful in facilitating that transition. I think I've made that request to CFRG before. I make it again now. If anyone has ideas there, would be interested. I was wondering if you had any thoughts about how, if there are ways that it seems like you've kind of parsed out kind of the NIST process and IETF/CFRG processes in fairly separate stacks here. I was wondering if you have any thoughts on how they could maybe support each other, if there's things that CFRG or IETF could do that would be supportive of the NIST process in terms of different perspectives, evaluating proposals, or doing interop testing or something like that.
Okay, yeah, thanks for that suggestion. It's an interesting idea. Maybe we could have some IETF folks attending the NIST workshops that will take place and feeding in requirements. I mean, the sort of requirements gathering phase is somehow passed already. There's a requirements document that's been published already last year, but there's probably still opportunities to influence if new requirements arise. So I encourage everybody here to go find the NIST call for proposals document at this website. Let me find did I go back past it already? I'm trying to find the URL. Well, you can find it online anyway. And there you can see the call for submissions, and there it talks about these kinds of requirements. So if something is missing, then IETF people should get involved. More generally than that, I'm not sure. Off the top of my head, I don't have any great suggestions for how we can complement what they're doing, aside from the things I already mentioned. I think I know for a fact that all of the key players in the research community in this are really focusing their efforts on the NIST competition. Maybe getting some of them to come here and give updates on what's happening could be useful. You want to come back?
Yeah, just real quick. I think that's a good insight. I think maybe that we have a little bit more of the industry players here, and so perhaps this could be a way to make that connection between the academic researchers and doing some more kind of operational testing in systems that are a little closer to production.
Thank you.
Paul Hoffman, two things that are related. One, when you said, well, I don't know how big the keys or the signatures might be, just for the people in the room, current estimates are they're going to be at least an order of magnitude larger. So we're talking about 50,000 bit keys and such like that, depending on signature sizes and such. Obviously, this is one of the things that NIST is considering on trying to minimize that. But if you've got a protocol running over UDP or where everything needs to fit in one packet, you should be very concerned about keys or signatures, which leads to the next one. So as Kenny gave a presentation for me yesterday in CFRG because I had a conflict, I've got a document called Draft Hoffman C2PQ, which is classical to post-quantum, where it has nothing to do with what will be chosen, but we have to sort of get an idea of how many. I'm looking for people to help. If you look at the draft, you'll notice it's completely full of holes and requests for input. This is not something that's at all baked. We need a lot more work done on it. We're going to be talking to other people in both in the physics side and in the crypto side. But in this room, we are going to want to know when should we be making the transition. And you gave a couple of examples of soon, longish term, never. And it would be nice if we as a group could have some parameters on that. So please take a look at that and talk to me if you have any ideas.
Thank you, Paul. Let me second what Paul was saying. I actually forgot to include it in my slides, and I meant to, a mention of the draft. That would be a great place for people to start contributing. Thank you.
Right. But, and again, just to be clear, it's super, super early in the draft. So lots of room for if you were looking for something to contribute, please do.
Thank you.
Phil Baker. Couple of points. I do have a degree in nuclear physics, and I don't think that quantum crypto is going to work because quantum key exchange will work because the engineering parameters are too hard. But I wanted to, one point is that we do have Lamport signatures, and they work, and it might well be worth baking in Lamport signature roots now, because that is one thing that we can trust and we don't need to do any more research.
Mm-hmm.
But going back to your original bit about the whole SHA-1 piece, CAs actually started moving to SHA-2 in 2008.
Some of them did.
Yes, and Russ helped me push one of them to do just that. The big problem was that the rest of the infrastructure wouldn't accept them until much later. And as a CA, I can't issue certificates that other people won't be able to read.
Sure, and the other side of the argument is that they wouldn't update their software because no one was issuing SHA-2 certificates. I mean, we know this chicken and egg situation is often the case in crypto deployment.
Yeah, and I did come up with a bunch of proposals to try and smooth through that deployment cycle that were rejected by the same people who then, when they could see the writing on the wall, come back and say, oh, we've got to get rid of this right now, and we've got to cancel certs that are already been issued. So, I mean, like the issues that you were pointing to on CAB Forum, that's actually got to do with the financial networks, and they have a bunch of stuff that they have put out and haven't been listening to anything. And so we've had to take a bunch of CAs offline. They're not part of the web PKI anymore to make use of that, and that's been a multi-million-dollar backwards. So
it's been a lot of fun.
Right. So yes, we've got to have a deployment plan for this, and we can start working on the deployment plan before we actually have any crypto.
Mm-hmm. Thank you. I think that's very much what Paul Hoffman's draft is about too. It's about starting to really strategize about that stuff well in advance. Thank you.
Stephen, great talk, Kenny. Thanks. So comment on a question. So the comment is, I think another thing the IETF could do is look at when we're dealing with data items that might still be sensitive in the far distant future and not do that. So rotate identifiers, don't have long-term things, et cetera, et cetera. A lot of this is in the application space, maybe more than in the IETF space, but I think it's still something the IETF could be doing, is knowing that if we're creating new long-term identifiers and those can be correlated with things, maybe we shouldn't do that.
Okay, I don't think it's just the identifiers though, it's also the plain text, right? And
yes, but most of the plain text probably isn't in an IETF context.
Okay.
And then the comment was, so you had a nice timeline that said, you know, sit back and relax for 7 years. The question is, what's the kind of IPR situation here, and have we got 27 years to sit back and relax?
That's a great question. I was reading the draft, just the call the other day. What did it say about IPR? It's definitely a consideration. I mean, NIST is obviously aware of it. I think they don't require IPR declarations. It's not, I won't say anything because I'm not sure, but it's certainly something that's on their mind. Maybe somebody knows. Yeah, does Quinn want to come and say something about IPR and NIST? If you can cut in front of you, Nick, that would be great.
I think we require the IPR to be declared.
Okay. Declared but not given up.
Yeah, not given up, but we hopefully prefer. It's not. Yeah. Okay. But you see, in practical words, if you have two things the same and one with IPR and one without, then.
Yeah. I know that there are teams who are targeting the NIST competition who are making their proposals as boring as possible from an IPR perspective. That's what my team is doing. So hopefully there'll be some proposals that are not IPR laden. We can hope.
Hi, Kenny. Nick Sullivan. Thanks for the investment advice on isogeny-based crypto. But something to point out that actually is pointed out by isogeny-based crypto is that the key sizes don't have to be extra large. You can actually, there are post-quantum schemes in which you trade a lot of computation with small key sizes for quantum computer resistance.
Right. I think that's a great point, and I promised to not put any equations on the slides, so I didn't get down to that level of detail. But my comment about isogeny-based crypto was mostly about the novelty of it, the newness of it. It really isn't in any sense battle-tested. Still very new technology.
Tobias Gonrum, Huawei. So when it comes to the timelines, I feel like in a quantum state. It may happen in 2030, it may happen in 25, it may happen in 35, or it may never happen. We will only find out once the quantum states have collapsed. However, like when you mentioned your point with the capture data now and read it later, I think that's one element. You should add one more thing. The devices we design, the protocols we design, they have lifetimes of 10 years plus. So I think that kind of leads us to this maybe crypto agility plus, that we need to design the protocols in a way that we can update them without too much breaking our necks in, let's say, 5 to 10 years time, if that state actually happens. And I think that's probably a requirement we need to consider now, just so we can manage the tail end if these incidents happen earlier than we expect them to. Would that be a fair?
Yes, absolutely. I think that's a great comment. Thank you.
Right. Thank you very much, Kenny.
Okay. Thank you.
Okay, so now we're going to have a talk on pretty easy privacy, not as easy to say, by Volker Burke.
We'll have this in a second. Some pilot error with the slides.
If there will be slides.
I will be bringing them up just very shortly when hopes.
Okay, I can introduce myself because I'm new. I'm Volker from Pretty Easy Privacy. We have a project trying to solve. Okay, this is a mic, but I can even ignore it. Okay.
Hug the mic, friend.
Well, good. I have testing time. Okay. Okay. Again, my name is Volker. I'm from Pretty Easy Privacy, and we are trying to solve a quite hard problem. It's the problem users don't need to get involved with crypto details at all to use crypto, and that on open standards.
Okay, here you go.
Thank you. So, yes, here we go.
Just tell us when you want to change slides. Okay.
Yes. We also, could you go back, please? We also applied a draft here, or supplied a draft here, where you can read some details. We'll come later to that. Next slide, please. The problems we're facing, I think, is quite clear. Unfortunately, there's way too less privacy in the internet, and we really think this is a big issue because the network could help a lot for civil rights, but if it's still like this, then we need to improve there. And what we're actually watching, where it's going to in crypto for users, is either it's going to proprietary platforms, which build some system which works quite well, but it's closed source. No one knows really what's behind the curtain. And on the other side, we have open standards, which are, yes, basically for email, some others, and which are quite hard to use. So that's the situation we found, and that's where we want to improve. And another one is we really believe that Jabber deserves gaining more users. Okay, next slide, please. So this is just an example of things we are actually working on and we need answers for. I will not go through all of them, but basically you can say there is lots of missing interoperability here, which gave us the idea to talk to you guys if you want to help here. And there is also things, well, we have basically either web of trust idea, which as a privacy activist I really dislike, because the web of trust means publishing a social graph, and this is exactly not what privacy wants. And on the other side, we have the hierarchy of X509, which is in a privacy view way better, but which ends up with trust anchors, which make issues. So our idea is that we start to do everything peer-to-peer and not server-based. And this is the core of the PEP idea, having a peer-to-peer implementation of everything. And we also want to add things, we're already working on it, which is hiding metadata, supplying pseudonymity and anonymity into our implementations and into other implementations. So this means extending formats, extending protocols, and so forth. And one really important thing, which is totally underestimated in my view, is we never managed to find a real standard for identity management. So we have very different ways to manage identity, and at least we need a mapping, or we can even define what pseudonymity means in a technical way. So yes, so what we want to achieve is a common concept to exchange keys and signal trust until the user is, PEP is a very user-centric project. We compare that with what the web browser guys do. That means we end up with something like a traffic light semantics. Next slide. Okay, so what are those guys already doing? We already have an implementation of automated key management locally and between devices. That's automated key management. We mean completely peer-to-peer. We mean generation, revocation of keys. We call it key reset, which is a little complex thing. So I need new keys because. And we already implemented a three-stage trust rating concept. We implemented SMAM and OpenPGP because open standards is highly important for us. So we want to be as compatible as possible. We implemented message formats which have a little more privacy properties. We implemented a first version of what we call key sync, which is a synchronizing of keys between the devices one user is owning. That means I have let's say a pad and a telephone and a laptop, and I want to share the same keys on all my devices, but no one others should have the keys for obvious reasons. So we implemented that, and we created adapters so you can use the implementation, because all what we are doing is free software, in common languages where applications are built. Next slide, please. What we also did is we just implemented applications to show that this is actually working and you can just download and try it out. So we did it for a couple of platforms. And what is still missing is we have a deal with the GNU. I think it was first time in history that GNU actually is giving out property instead of taking it in. And the first guys, they did it is us. We are actually co-owning now. We have ownership on GNUnet as PEP Foundation. And we are building with it the DHT-based onion implementation based on the subsystem of GNUnet, which is called Cadet. And yes, we have way more work to do because we need to synchronize more things. So, for example, we already synchronized keys. It would be nice to also have the trust synchronized. If you trust something on one device, it would be nice that it's trusted on the other device for obvious reasons. Next slide. So this is an example of that key sync topic, how it's working. Basically, we are using ASN1, and you will kill us for that. I already heard that. There's a very good reason why we need pair, because we need it as small that it fits in a Twitter or in an SMS. So that's usually, that's really the boundaries, and that's the thing we found which actually works there. And we are doing key sync with such device groups, also already multi-platform. The green box is what we already implemented, and now we'll want to propose. We will write drafts so it as internet standards, and the missing things is what we're actually doing work. Next slide. So where can you guys help us, I hope, or we can be a new member of the family, which I hope more. This is, of course, there is a draft for MIME-based message formats, which is from the IETF, and we already implemented that for being compatible in our engine. But unfortunately, this draft has major issues in our concept, and yes, let's say we are not very happy on it. That is the reason why we will do another one, and let's work on that. And we have the hope when we design network protocol families, which could be helpful not only for PEP, but for many, many protocols like doing a peer-to-peer key sync implementation. We have the hope that we can make a standard that this really works over platforms and protocols. Yes, also the mappings, we are using email and Jabber for inbound communication of things like key sync. And so we want to standardize that so we don't get into the mess that the different implementations will not be compatible. And there's even things like URI schemes we designed because internally we are using URIs for addresses. Next slide, please. There's also lots of future topics we hope to find people being interested in the IETF, which is identity mapping, calendar mapping, as already mentioned, and also what we call key mapping, which is we have text message transports. We call them transport. Email is a transport for PEP, which means we have such things where a PKI is just so huge and you cannot use it on such small things. Think of SMS as a primitive example. And so we have automatical mapping onto symmetrical temporary keys. And of course, we're also working on non-MIME message formats. I already mentioned Jabber. I don't know how much they will fit. Next slide. So what is our hope to find here? Yes, we really want interoperability, and I think this is the right place to ask for it. And of course, we need lots of critics. We need your hard critics because we are just doing it on our own and just put an implementation on the table here. And it would be nice to hear the opinion of experts in these fields where we are right and where we are wrong, right? And what we also hope is PEP Foundation is way too small to offer a management of open standards. So we have the hope that the IETF wants to jump in. And because I have no clue of the IETF, I'm very happy to find people help me here. It would be so nice if we get some guidance furthermore how to achieve something like that. Next slide, please.
Actually, I believe that the comment that just came into
yes, please.
Would reflect now. From Aaron Zauner, has the PEP Foundation ever taken a look at the work in the Utah working group with regard to email security, reporting, and UI/security improvements? As far as I know, PEP is implementing a kind of overlay for popular clients based on either SMIME or PGP. Utah meets later on. Please join. So I believe he's suggesting that that would be one place that meets the requirement in your last slide, last bullet, which is where would this take place? Utah appears to be one such place.
Oh, that's great input. Thank you. I think we'll do that. Okay, so because I only have a quarter of an hour, I know the project is way too complex to explain it in a quarter of an hour. I would love to invite people. We do a barb-off in room Terraca this evening, and if you have time, feel invited, and this for sure will end up in a bar, I can guarantee that. Thank you.
Hi, Paul Wouters. So I'm not exactly sure what you're proposing. Is this an effort to strengthen a whole lot of protocols within the IETF to do better security? Or are you suggesting that this is a whole new federated area that we're building? Or are you some new centralized phone book that has all these privacy and anonymity features inside? Like, I'm really confused.
Okay, first, we never centralize. We do only peer-to-peer, and there is no central infrastructure, and the PEP Foundation is managing nothing.
Okay, so then, hi, I'm Edward Snowden. Here's my identity.
Yes. Which is possible because we don't manage identities. I talked about mapping of identity management of other people, which they do in different ways, into each other, so there is interoperability. It's not meant that PEP Foundation will not provide a namespace where you can register. That's not what you're doing. I confused you even more? Oh, well. Okay.
So Martin Thompson, that actually helped a little bit. I read your draft. I've looked at your website in some detail, and I have to confess that neither of those things helped me the slightest bit understand what you're trying to do. I saw some statements about grand principles, and I saw some code, but I didn't see anything connecting the two of them, and I didn't see an architecture or anything. I think you've actually got a lot of things that you're asking us to do here, and this presentation was really quite helpful as well in helping me sort of understand where you're going. But I suspect that what you're going to need to do is talk to a few people here this week, and I think unfortunately I'm occupied otherwise for the Barboff, but I would love to come. But you need to ask these people for help because you're actually asking for a number of different things.
Yes.
And what the people here would like to see is how what your goals are, and in a very concrete way, how those goals fit together. If you have an architecture, what that architecture looks like and how the various pieces fit together, and where you have identified deficiencies in the individual protocols that you're using, what those deficiencies are, and how you propose that they would be fixed. And this is a massive project, I have to say. The number of things that you had on these slides is frankly frightening, and it would be, I respect if you can make any progress on this at all.
There's working implementation already, which you can download and try out.
So I caution that there's a very big difference between implementing some code and shipping some code and actually getting to the point where you have interoperability. And that's a long, hard battle. And I roundly congratulate you for even attempting that. Thank you.
Well, thank you. And you're so right, by the way. It's really a hard battle.
Phil Baker. Yeah, I've been following this for quite a while now, and I like it. And I'd just like to point out, at the moment, there are a lot of usable, secure end-to-end messaging mechanisms around. You know, we've got Signal, WhatsApps, and so on. There are two problems with that. One is that they're all single silo models. So in order to talk to somebody who's on Signal, I've got to get Signal.
Yes.
And so that immediately cuts down the community I can talk to. The other problem that you have is that they're all being sold as ways around government coercion. And the thing is that if you require everybody to run the same app from a single provider, the application is a point of coercion, even if your crypto is end-to-end secure.
Yes.
And so if we're going to get to the point where we have a system that is resistant to government coercion, it's got to be based on open standards such that the implementations can be audited, and the protocols have to be designed in such a way that when you are dealing with a messed up version of a coerced version of the application, it tries to talk to a non-coerced, then it's got to become apparent. And one of the things that I had when I talked to somebody very senior in one of the agencies formerly, his advice was nobus, nobody but us. In that the thing is that they're very willing to mess around with crypto and applications or whatever, but they're very adverse to having their messing up being detected.
Sure.
And so that's the thing that we've got to work for. Whether this, I've got problems with this particular implementation. I think that maybe we need to go to a consensus algorithm that allows us to centralize without being centralized, but it's good work. Thanks, Lee.
Thank you.
Okay, thank you. So next up we have Dmitry, and I don't want to try to say your last name. Oh, on certificate limitation profile.
Second, I'll have your deck up.
We'll have your, yeah.
Next slide, please.
Let me bring it up actually in the preview. Sorry, not my laptop.
Okay.
Slideshow.
Okay.
There you go.
I will speak about my proposal to standardize application level application supported list of certificate limitation. Next slide, please. Current state of trust is in PKI world is mostly defined by RFC 5280. We have binary model of trust. We have a set of trusted CAs. We have CRL and OCSP validation, and we have CA-driven revocation. The CA-driven revocation does not always fit the purposes of real world. For example, here is the link to a presentation made for CA browser forum. Next slide, please. And one of the most significant cases of not fitting current model to the real world is the case of Google versus Symantec. When Google found that Symantec misbehaves, the company suggested to limit certificates issued by Symantec. It suggested to reduce the accepted validity period, to gradual distrust to current trust that Symantec issued certificates, and so on and so forth, and even to remove the recognition of extended validation status for Symantec issued certificates. Next slide, please. Now, when application wants to limit trust, it has, in fact, 2 or 3 options. Well, application can specify which trusted CAs are valid in its context. It can turn off CRL and OCSP validation, and we have problem what shall we do when OCSP is not available. And in case we have we need flexible limitation, for example, when one of CA is too big to fail, we have to hard code them. Next slide, please. I propose a solution, certificate limitation, named certificate limitation profile. It's a list that can be distributed with the application or by the application as a part of application bundle. It should have serial-like syntax. It should be cryptographically signed. And if this proposal finds interest and implemented, the users, the author of application can use shared code base instead of application level hard coding. This will allow to avoid some common mistakes in validation. Next slide, please. So what can be stored as examples of such limitations? At first, we should say whether the limitations are applied to certificate itself or its descendants on the chain of trust. And for example, we can say that we should not trust certificates issued after this or that date. We should not trust the certificates matching the profile
after the concrete date. We can limit the validity period of certificates. We can say which X509 extension should be ignored. We can say which extensions should be required to trust the certificates. For example, for WebPKI, it's the common case is certificate transparency related extensions. We can, as it was suggested many times, limit domain names by the CA, like name constraints. Next slide, please. The proposal implies changes to the verification process. After building chain of trust, we go through it and apply limitation to the match inserts, and if specified in the profile, we apply them to its descendants. If we find that the certificate should not be trusted, we stop verifying and return that it's untrusted. Next slide, please. And so instead of hard coding many limitations at the application level, we can limit very small set of check that we have CLP in use, that the CLP we operate is fresh enough to avoid rollback attack, and that CLP is signed by correct trust unsure. Thank you very much.
Martin Thompson, the agenda doesn't have a link to a draft.
Sorry, my fault. I will provide the link to.
Just a request to the chairs on.
Yeah, my fault.
Yeah,
not your fault.
So I don't know what this is, but having said that, what exactly at the mic? I certainly haven't read this. But you're describing a number of things that has a significant amount of overlap with a number of existing deployed mechanisms, like public key pinning, and we implement a thing called 1CRL. There's been a proposal to use recursive Bloom filters in combination with the certificate transparency log to have an exhaustive list of certificate revocations. Why would this be superior?
Well, the certificate, the CRL profile is CA driven, for example.
Sorry, I missed that.
The CRL are CA driven. The CRL should be issued by CA. This profile can be issued by the application author.
This is something that 1CRL does.
Yeah.
Yeah, so there are application vendors, Richard Barnes, there are application vendors doing this today. So Chrome, Google for Chrome produces CRL sets, which are basically largely overlapping with kind of the limited subset of the functionality you described. And Mozilla produces a thing called 1CRL, as Martin mentioned, for Firefox. And so the question is, those are proprietary things, but they're between a vendor and its application. So I'm curious, like, what's the value of standardizing this and adding all this additional functionality?
Well, yes, it's a similar functionality to the one you described. It's just try to formalize the proposed syntax.
Hi, this is Daniel Kahn-Gilmore with the ACLU. I'm also work on the Debian project. I don't know if you're aware of the P11 Glue project, which has a storing trust policy specification they've been working on that fits what you're doing, I think, almost exactly. And the use case, Richard, is that there are a bunch of different things that actually check certificates, and the rules are subtle. And so if you can actually build a particular API, then you can encourage people to not rewrite their own. So there is, I think, definitely merit in this kind of work, but there is existing work that does this, and I'd be happy to try to point you to it and connect you to it if it's useful.
Thank you very much. It will be great.
Rich Saul's, I guess, OpenSSL affiliation. Yeah, it's great that 2 or 3 programs on the internet can do really fast and really precise checking of revocation, but I'd like to see this extensible to all sorts of things, so not just the browsers, but there are many web PKI programs out there, so I support this. It'd be interesting to come up with a standard data format. I've had some discussions with some of the Linux vendors about doing that, so yeah, I encourage this.
Yeah, Martin Thompson, as someone involved in one of the projects that has one of these things, we'd certainly be willing to participate. We already collaborate with Google, who runs one of these things. Opening up a standard for this wouldn't necessarily be all that onerous, and I think we'd be open to that.
So there was Richard Barnes again. So thanks, DKG, for the clarification there. I think, yeah, I can see there could be some value to this. I think at least a soft prerequisite for this work is going to be, well, a prerequisite for the work to be successful is going to be some notion of who is trusted to distribute this information. In the vendor to its application space, it's kind of clear because you trust Google for Chrome, you trust Mozilla for Firefox. It's not clear what you would do for, say, OpenSSL or Debian. So it seems like there needs to be some work done on that aspect of this problem as well, if it's going to be worth developing a format.
Eric Riscorda from the floor. As someone else who works on one of those projects, there are actually two problems to solve. One problem is the policy problem of indicating like which anchors you trust and which intermediates to revoke, and the other is to address the problem of identity certificates. And the problem there is data compression, because the number of revoked identity certificates is far too large to actually send over in any format that looks like this at all. So in order to solve the entire problem, you've got to solve that problem as well. There's been a bunch of work on that, but.
Well, for the first problem, I expect that the trust anchor will be distributed with the application that implies using CLP. For example, hard-coded and checksummed. But yes, it's a common problem of distribution trust anchor, and I hope we can use common methods for it.
Sure, but similar to the trust anchor problem is actually harder in that the determining the hard coded actually is terrible because it makes it very, very hard for a new CA to enter the market. I'd almost rather, if I had to decide between solving revoking intermediates and adding trust anchors, I might actually prefer to do the second one rather than the first.
Okay, so thank you, Dimitri. And could you send a link out to SAAG, and I will update the agenda to include it as well.
I will send it to SAAG. Thank you very much.
Thank you. Now we have 20 minutes left for open mic. Uh-oh.
Great.
What? It could be something different.
But it will be. But it will be.
Hi, Stephen Farrell. So there was a bit of a fuss yesterday in the TLS session, and hopefully we killed off one more bad idea. So without getting into the details of that, which I don't think are right here, and the TLS working group are continuing to beat down more bad idea fairies, I guess. If the TLS working group went crazy, I think that wouldn't be in their charter, and they would need to recharter to do the crazy thing. And also, I think you heard from Lars and from Kenny that clearly such changes to TLS would have big impacts outside one working group and outside the security area and in the other parts of the IETF. So I'm just wondering what you guys think about that.
So nothing's been adopted yet. There's still discussion. I think it remains to be seen what will happen. If new proposals will come to the table that maybe are better and maybe they have nothing to do with TLS is one thought I had. If there was something specific to the data centers, perhaps. That's one thought that I had after listening to some of the conversations and, queuing off of other people's ideas and thoughts, maybe there's an opportunity for something data center specific. And then you could design just what you need and it wouldn't interfere with TLS or, our internet level applications for encryption. I don't know, that's one thought I had.
Yeah, which I think makes sense as well, yeah. But on the issue of...
But the working group decides, right? So,
yeah.
So if they conversation's still happening.
So I guess the specific question for you is, if they adopt something like this, do you consider that within their current charter?
You're the AD.
Yeah, I have to go back and reread the charter. I'm sorry. I will do
I
that.
can
though.
suggest an answer.
What would that be?
So
I would have to go back and reread it carefully as the AD. So, and obviously, we follow what the working group wants to do. So we'll see what they ultimately decide, right? So there's more conversation happening.
Sorry, I thought you were going to.
Yeah, no, speaking not as AD, I don't believe that draft green would be within the Tails Working Group charter at present.
Right. Okay, which means that if they did try and do something crazy like that, it would need a recharter. Because the reason I ask is because at that point, the IETF gets to have a say, as opposed to just the people in one room or the people on one mailing list.
The reason I'm trying to be precise about this is it's possible some other thing might be within charter.
Granted, sure.
I don't think draft green, however, would be within charter.
Right. Okay.
Any other questions?
Sorry, probably less interesting. But still, back to Kenny's presentation, there was a quantum random oracle mentioned in CFRG, and you guys need theoretical models to prove security. So I wanted to ask probably your personal opinion on whether these models exist, are reliable, and are something that NIST can base the evaluation on.
I know nothing about this, Kenny.
Yes, yes, and yes is the answer. So yes, they exist. What was the second part again? But there was definitely three yeses. Stable, reliable. Well, the quantum random oracle model is something we're still getting our heads around. There's a few experts in the world who know how to work with it, but the group of people who can is growing in time. It's basically an extension of the random oracle model, which is some kind of abstraction we use for modeling hash functions and security proofs, taking into account quantum capabilities of an adversary. So it should become a standard tool for the analysis of all of the NIST proposals. And is it something that NIST can rely on and use? Then yes, I think so. Hope that helps.
Anything else? All right, enjoy the rest of your day.
I'll take this back.
Thank you. Thanks for having that.
No,
and doing that.
I appreciate that you use your laptop generally, so I felt maybe I could do is go get it.
Mine is just, too many variables. I should hook it up and see if I can get it.
I fucking hate using my own laptop for this. Sir. Yes. Oh, this was it.
Thank you for sitting right where you sat.